Hey everybody, it's Monaco here. I'm not sure if you can see my sweet black eye, but we're doing kinetics and equilibrium vocabulary in this lesson. This is for you, those of you who missed class or need to study and review before the end of the unit. Learning targets for our vocabulary is the same. Can I define the defined and the specialized vocabulary of this particular unit? So let's get to it, brass tacks. Kinetics. Well, what the heck is kinetics? Kinetics is motion and energy. There's cold and there's hot. Okay, kinetics is going to focus on the rates of reaction. So cold things react slower because of the motion of the particles is very low, doesn't have much energy. Hot things react quicker because the motion of the atoms is higher and it has plenty of energy to cause a reaction. Reaction rate. Rates are times. We use stopwatches to measure rates. We see how quickly something occurs. And time versus reaction progress is typically the way we represent this. Collision theory. If you look carefully, you can see particles colliding, and when they do, some react. Okay, so collision theory is an idea that describes what it takes for a reaction to occur. There's 4 or 5 steps in there, and it always starts with the reactants, the ingredients, colliding with each other at the atomic level. An effective collision is part of collision theory. In order for a reaction to occur, that first collision must happen in the right orientation with the right energy to break the chemical bonds of the reactants and form the chemical bonds in the products. So collision of reactants with enough energy and proper orientation to start a chemical reaction is known as an effective collision, which would lead to a chemical reaction occurring, and that is kind of what we're studying this unit, what allows a reaction to occur. A catalyst. A catalyst is an ingredient, and in this chart you see the dotted dashed red line is the progress of a reaction that has a catalyst added to it. So a catalyst actually is a substance that speeds up the rate of a reaction, but itself is not consumed by the reaction. It's kind of like a traffic cop directing traffic. There's a log jam, a bottleneck with all these cars, but once you put a catalyst, a traffic cop in there, all that log jam disappears because he or she directs traffic and makes it happen very quicker. But that person individually isn't consumed as part of the reaction. They're not in a car themselves. They're standing there making sure everything goes accordingly. Thermodynamics is a big scary word, and this is a picture of what they call a heat engine or a steam engine. And thermodynamics is simply the study of entropy and enthalpy, so heat and randomness and disorder in chemical reactions. Thermodynamics describes why reactions occur, and that's why we put the word in here. A potential energy diagram. This is the typical example, and it is usually going to ask you to label or identify one of the portions of this graph. It is a graph that shows the difference between the energies of the reactants and products, as well as things like the effects of adding a catalyst and the overall change in heat of the reaction, which is what our next word is. This is a great animation describing all of the parts of a potential energy diagram. The heat of reaction is the difference between the reactants and the products. You find that out by taking the energy of the products on the right-hand side and subtracting the energy of the reactants from the left-hand side. If you get a positive number, the reaction's endothermic. If you get a negative number, the reaction was exothermic. Enthalpy. Well, enthalpy is delta H, the change in heat. So enthalpy is a fancy word for heat. It's the heat of a reaction. You find it by taking the heat of the products minus the heat of the reactants. And these can be found by looking at potential energy diagrams, or if the reaction's in table H or I. Let's see here. Got to make sure that's not a typo. H, I think H is for heats or reactions. No, it's I, table I. There's a typo there, so fix that. Energy diagrams or table I. Entropy, randomness and disorder. On the left, we have a highly ordered sphere of particles. An increase in entropy makes more disorder. So it's a measure of the disorder in a system. Thermodynamics laws favor greater disorder. So reactions that produce gases or more disorder are favored by the laws of thermodynamics. Forward reaction is when we look at a reaction from left to right. Reactants make products. The typical reactions we've been seeing all year long. They are forward reactions. A reverse reaction is new. This is the reaction moving right to left. This is products to reactants as well, but these two overlay and we get what we call an equilibrium. So reactions can run in reverse, is my point. The activation energy of a reaction is how much energy it takes to get things going. The particles of a reaction have to collide with enough energy to break their bonds and form new ones. So the activation energy represents that, how much energy it takes to get the reactants to the activated complex where all that bond breaking and forming occurs to make the new products out of it. The activated complex is that moment at the top of the potential energy diagram where all the atoms that are involved are in flux. They're changing from the reactants into the products, and so we call it a complex because it's a complex scenario. Begins the formation of the products. There's your definition. You can write that down. Okay. Equilibrium. Equilibrium is the term that we use to describe dynamic changes without much overall, how do we say it? Well, it's a state where reactions are happening in both forward and reverse direction at the same time. So we have a forward reaction going from left to right, and we have a reverse reaction going from right to left. And this is shown in equations with a double-headed arrow. And that is one of the main features of this unit, that reactions can go in both directions at the same time. It's called dynamic equilibrium. Physical equilibrium. A physical equilibrium is where we have like solids, liquids, and gases. Kind of the phase equilibrium is another term for it. So it's the rate of melting equals the rate of freezing. So in our heat unit, when we did heating and cooling curves, the flat portions of our heating and cooling curves were physical equilibriums, where the rate of melting and the rate of freezing or the rate of boiling and condensing were consistent and constant. Chemical equilibrium, however, is slightly different. It's the rate of formation of the forward reaction equals the rate of the formation of the reverse reaction. So both reactions are happening at the same speed, but in opposite directions. It's kind of like a highway where everybody goes exactly 65 miles an hour in opposite directions. A solution equilibrium is the rate of dissolving versus the rate of crystallization. So in all saturated solutions that we've seen, like in our solutions unit, has crystals sitting on the bottom of a test tube. For every crystal that dissolves into the liquid, a crystal forms from the liquid onto this existing solid at the bottom. We call that a solution equilibrium. Le Chatelier's principle is illustrated in this short GIF that shows how when you change conditions, you can get a change in your reaction. So when you stress out an equilibrium, the reaction itself changes. And it's difficult to see, but that gas in that tube is actually getting lighter and darker based upon the temperature of water that it's placed in. So a reaction at equilibrium will shift to regain its equilibrium if subjected to a stress like heat, pressure, concentration changes. So equilibrium stresses and shifts are what Le Chatelier's principle governs. When we change a concentration, a heat, or a pressure, it causes a change in the products or the reactants, which shifts an equilibrium towards the right or the left. And that is one of the things that we'll be studying this unit. And that's all, folks. So I'll see you in the third lecture, which is our first true lesson of the unit. Adios.